Usually when we talk about engineering a physical structure, like, say, a bridge, there is this expectation of physical limits.
Right, yeah.
You run out of steel, or the ground simply can't support the weight, and the project just stops.
Gravity and physics act as natural, unavoidable boundaries. It forces a very specific kind of planning. I mean, you can't just keep adding lanes to a bridge or floors to a skyscraper without reinforcing the foundation. The physical world pushes back.
Exactly. But then you step into the world of software engineering, and suddenly it is like gravity doesn't exist anymore. We are looking at a building landscape that is limited only by our own cognitive limits.
Oh, yeah. It is the absolute definition of infinite conceptual complexity.
Right, just our ability to keep track of the sheer volume of logic.
The real bottleneck in software has never actually been writing the code itself. It is managing the massive, invisible structures we build in our minds.
And that invisible structure is exactly what we are mapping out today for you. We are using your notes from Class 22 and Class 23 to trace the leap from basic abstraction to object-oriented design.
Yeah, you have studied object-oriented design in prerequisite courses, so our goal here is really synthesizing that knowledge. We are looking at the big picture of why these tools exist before you dive into how different language families implement them.
Okay, let's unpack this. To really understand why we have objects in classes today, we have to take a trip back to the 1970s.
Right, to a period famously known as the software crisis.
Yes. Hardware was getting exponentially more powerful, which meant people were attempting to write much larger, much more ambitious programs.
Yeah, and the issue was that the programming languages of the time were primarily imperative. They just executed lists of instructions from top to bottom.
Like a straight recipe.
Exactly. And as programs grew, the logic became incredibly tangled, heavily relying on global variables that, any part of the program could change at any time.
So if you pulled on one noodle, like one variable or function, you had no idea what other part of the program you were going to break.
Because everything had access to everything else.
The complexity had basically outgrown the human mind's ability to divide and conquer it. And this is where a computer scientist named Barbara Liskov enters the picture.
Her work fundamentally shifted how we structure code. She realized that to survive this crisis of complexity, developers needed a way to represent high-level concepts using common data and functions,
while completely hiding the messy implementation details from the rest of the program.
Exactly. And she recognized the need for what we now call abstract data types, or ADTs.
And her team didn't just, theorize about it. They created a whole new programming language called CLU, specifically to demonstrate a syntax that supported these ADTs.
To appreciate what a leap that was, look at the two goals of an abstract data type. First, you declare variables while hiding the details of the type's representation.
Meaning you lock down the internal member variables?
Yeah. And second, you provide a specific restricted set of operations for that type.
I always hear the TV remote analogy here. Like, you get buttons on the outside, but the circuit board is hidden inside a plastic shell.
Right.
But mechanically, how does that plastic shell actually work in code? I mean, How do you physically stop another part of a program from messing with those hidden variables?
Well, what's fascinating here is that it comes down to access modifiers instructing the compiler. When Liskov's concepts evolved into modern languages, they introduced keywords like private or protected.
Okay.
So when you mark a variable as private inside an ADT, the compiler literally refuses to generate machine code for any outside instruction that tries to access that specific memory address.
Wow, so it throws a fatal error before the program even runs.
Exactly. It is not just a suggestion, it is a structural barrier enforced by the compiler.
That gives the programmer building the ADT incredible freedom. They get implementation decoupling.
Yeah, they can completely rewrite the underlying logic. Maybe swap out an array for a linked list to make it faster. And as long as they don't change the names of the public methods, the rest of the program has no idea anything changed.
What's fascinating here is the psychological shift this causes, right? It provides reliability because you can't accidentally short-circuit the internal data.
But more importantly, it provides simplicity. A programmer using an ADT doesn't need to dedicate mental bandwidth to tracking hidden variables. They just focus on using the data type through its provided methods.
The cognitive load is drastically reduced. So ADTs gave us this protective shell. But obviously, software kept getting more complex. What happens when you need an ADT to be flexible?
Right, because an abstract data type only works with the specific types defined by its interface.
Like, say we build an ADT for a stack. It is great for holding integers. But what if I need a stack that holds text or video files?
If you have to write a brand new ADT from scratch every single time, you're just creating a different kind of clutter. Hard-coding a stack to only accept integers traps you.
So this forced the next major evolution: parameterized abstract data types.
Yes.
This is what Java programmers know as generics. It is that syntax with the angle brackets, like a less than sign, a data type, and a greater than sign.
A parameterized ADT allows the user to control the interface data types at the exact moment they create a specific instance.
So instead of creating 50 different stack data types for 50 different kinds of data, you just write the logic once as a parameterized stack.
When you instantiate it, you declare, this is a stack of integers, or, this is a stack of strings.
Mechanically, that seems like a massive upgrade for type safety.
Oh, it is. The compiler is now maintaining a strict lookup table. If you declare a stack of integers and you try to pass a text string into it, the compiler checks the angle brackets, sees a mismatch, and just stops the build.
And I don't have to guess what data type I'm getting back out either.
Right. It is worth noting, though, an interesting historical quirk regarding how Java handles this under the hood. Because Java added generics later in its life cycle, the implementation had to be backward compatible with millions of lines of existing older Java code.
Okay, that makes sense.
So the underlying Java bytecode, the virtual machine language that Java compiles down to, actually has no physical way to represent generics in memory.
Wait, really? So how does it enforce the safety if the bytecode doesn't even know what a generic is?
Through a process called type erasure, the compiler does all the heavy lifting during the build phase. It checks every single generic interaction to ensure perfect type safety.
Right.
But once it confirms the code is safe, it literally erases the generic type information. It deletes the angle brackets before generating the final bytecode.
Just deletes them.
Yeah, it replaces the specific types with generic object references, adding invisible casting operations. It is a fascinating compromise in language design to avoid breaking older systems.
That is wild. The compiler acts like a strict bouncer at the door, and then once you're inside, it just burns the guest list.
Pretty much.
Okay, so we have parameterized ADTs, making things flexible, and we also have encapsulation constructs to organize them, like namespaces in C++ or packages in Java.
Right. It is essentially putting all your ADTs into neat little folders to prevent naming conflicts.
It groups logically related code at a higher level, creating a clean architecture. But I have to push back here, though.
Okay.
If we have parameterized ADTs that are perfectly type-safe, and we can group them into neat little packages, haven't we solved the complexity problem?
You would think so.
I mean, I can hide the data, make it flexible, and organize it. Why do we even need object-oriented design?
Well, it looks like a complete toolkit until you encounter systems where concepts are causally related rather than isolated. The limitation is that ADTs, even packaged ones, are totally independent islands.
Ah.
Think about the banking system problem mentioned in your notes.
Okay, let's look at that. Imagine you are writing a massive banking application using just ADTs. You create an ADT for a checking account.
Right. It has internal data for the balance and account number and public functions to deposit and withdraw.
Then you need a savings account. It also needs a balance, an account number, deposit, and withdraw functions, but it adds an interest rate.
Because they are independent islands, you essentially have to copy and paste the logic from the checking account ADT into the savings account ADT just to add that one new feature.
And copy-pasting code is a massive maintenance nightmare.
Oh, absolutely. If you discover a logic flaw in the withdrawal math of the checking account, the compiler won't help you find the identical flaw you pasted into the savings account.
Or the corporate account. You have destroyed your ability to reuse and maintain code efficiently because you have no way to tell the computer that these concepts are related.
That structural ceiling is what necessitates the leap to true object-oriented programming, or OOP. We needed a mechanism to relate concepts hierarchically.
Right. But before we map out how it solves the banking problem, we need to clarify the terminology shift. When moving from procedural abstraction to OOP, what we used to call an abstract data type becomes a class.
And an instance of that class in memory is called an object.
The hidden variables representing the state are now attributes.
Right, and the subprograms manipulating that state are methods.
And crucially, when you invoke a method, it is referred to as sending a message between objects.
Which brings us to inheritance. This is the core feature that solves the banking problem.
The textbook analogy is always a biological family tree, passing down traits. But mechanically, I think of it more like 3D printing from a master file.
Oh, I like that.
Yeah, because if inheritance was just copy-pasting code, it wouldn't fix our maintenance issue. But it is not a copy, it is a live link.
That is a highly accurate way to visualize the mechanism. The base class, the superclass, or parent class is the master file.
And a derived class, the subclass or child class, is linked to it.
Right. It inherits all the attributes and methods of the parent, but it can add new ones or override existing ones.
So in our banking system, we create a generalized account superclass with the deposit and withdrawal logic. Our savings account subclass just links to it. We only write the new code for the interest rate.
Exactly. So if you find a bug in the withdrawal logic, you fix it once in the master account class.
And the next time the program compiles, that fix automatically cascades down the live link to every single specialized child class.
It is deeply elegant. And this hierarchical linking allows for powerful abstractions like abstract classes and abstract methods. The notes use a ground vehicle example to illustrate this.
Right. Let's say we are programming a traffic simulation with a generalized superclass called ground vehicle. Any vehicle must have an accelerate method.
Right, but you can't write the implementation code for accelerate at the high level of a generic ground vehicle.
Because the physical mechanism doesn't exist yet.
Right. Exactly. Accelerating a gas-powered car requires sparking cylinders. Accelerating an EV requires supplying current to a magnetic motor. Or, saying giddy-up to a horse.
So you cannot define the implementation.
Right, so you create an abstract method called accelerate. It has no code body. It is merely a structural promise. It tells the compiler, any subclass that inherits from me must provide its own unique logic for how to accelerate.
Because the ground vehicle class contains an incomplete method, the class itself becomes an abstract class.
Which means the compiler physically won't let you create an instance of it.
You can't spawn a generic ground vehicle into your simulation because if you sent it an accelerate message, it wouldn't know what instructions to execute.
Exactly. You can only instantiate the specific subclasses that have fulfilled the promise.
But wait, this brings up a mechanical question. Dynamic binding. The notes mention this is how OP handles the messaging.
Yes, dynamic binding is the engine of polymorphic behavior.
Okay, but how does the computer actually keep track of that? If I have a list of 100 generic ground vehicle objects in my simulation, and I tell a loop to call accelerate on all of them,
right,
the compiler doesn't know ahead of time which ones are EVs and which ones are gas cars. It is just looking at generic references. How does it run the right code?
Well, instead of hard-coding the memory address of the function during the compile phase, which is static binding, the program maintains a hidden lookup mechanism at runtime.
Ah, great.
When the loop sends the accelerate message to an object, the system doesn't look at the variable type. It looks at the actual object sitting in memory at that exact millisecond.
Wow.
It checks the object's internal metadata, finds the specific specialized method belonging to that EV or gas car, and routes the execution there dynamically.
It is figuring out the routing on the fly millions of times a second. That is incredibly powerful, but it leads to a huge vulnerability.
How so?
If we have these incredibly complex, dynamically routed family trees, how do we keep developers from making a complete mess of them? Because it seems like you could inherit things that don't make sense just to steal some useful methods.
This brings us back to Barbara Liskov, specifically the Liskov substitution principle, or LSP.
Okay.
It states that any subclass must be able to be substituted for any ancestor class without breaking the program or causing unexpected behavior. The notes refer to this as strong behavioral subtyping.
Which means it is not enough that the method names simply match for the compiler. You have to guarantee semantic interoperability.
Exactly. If a superclass method promises to always return a positive number, the subclass overriding that method cannot suddenly start returning negative numbers. That violates the invisible contract.
Here's where it gets really interesting, though. The notes explicitly say that sometimes, in the real world, developers deliberately ignore the principle of substitution just to achieve code reuse.
Yes, they do.
Is it really that bad to cheat the system? I mean, if inheriting from a totally unrelated class saves you writing 500 lines of complex mathematical code, isn't that a net win for productivity, even if the semantic relationship is technically wrong?
This raises an important question about the long-term health of a codebase. While OOP languages generally cannot force you to obey the principle of substitution, it relies on programmer discipline. Ignoring it creates a system that basically lies to other developers.
Because of the dynamic binding we just talked about.
Exactly that. If you pass a cheating subclass into a function that expects the superclass, that function trusts the object will behave according to the superclass's semantic contract.
Right.
If the subclass behaves unexpectedly, say returning that negative number, the dynamic binding still routes the execution flawlessly, but the logical output corrupts the system. You get bizarre cascading bugs because the object is masquerading as something it fundamentally isn't.
It is like putting the plastic shell of a TV remote over a garage door opener. Syntactically, it has buttons, so the user knows how to interact with it. But semantically, pushing the volume button opens your garage. The routing works, but the result is total chaos.
That captures the danger perfectly. And these philosophical choices about abstraction and strictness ripple directly into language design issues. Language creators have to make hard mechanical trade-offs.
For instance, do you build a pure OO language where absolutely everything is an object?
Right, a language that is completely orthogonal. The notes give the example of 204.3 round.
Oh yeah, in a pure OO language, even a literal decimal number is a full-blown object, and you send a message to it to round itself.
It creates incredible logical consistency, but the mechanical downside is the performance hit.
Because of the routing.
Yeah, message passing and dynamic binding require CPU cycles to look up those execution routes. If you are doing millions of mathematical operations a second, and every single number requires a dynamic method lookup rather than a direct procedural memory manipulation, your application slows down significantly.
Language designers also have to figure out how to handle memory allocation for all these objects, right? Deciding between the stack and the heap.
The stack is incredibly fast and structured, but it forces you to know the exact size of your data at compile time. Object-oriented programs, with their dynamic binding and flexible hierarchies, heavily rely on the heap.
Because the heap allows objects to be created dynamically while the program is running, growing, or shrinking as needed.
Exactly. But the trade-off is that the heap is chaotic. The system has to hunt for free memory space, and more importantly, it has to clean it up.
Which introduces the overhead of garbage collection.
Yes. The system has to periodically pause execution, scan the entire heap for objects that are no longer linked to anything, and clear them out to free up RAM. Language designers have to weigh the immense developer convenience of OOP against the physical CPU cycles required to manage its invisible structures.
Speaking of managing invisible structures, what does this all mean for you right now? If getting these class hierarchies wrong causes the chaotic bugs we just talked about, it makes perfect sense why this week's assignments are so crucial.
Absolutely. Understanding these hierarchies is exactly what you will be mapping out this week.
Let's look at how you'll be applying this because you have some critical deadlines approaching. First up, this Sunday, April 5th, your Week 10 journal entry is due. Keep the 2-1 rule in mind.
Right. Your entry must be a minimum of 2 paragraphs, and you must include at least 1 quiz question.
Following that, Monday morning, April 6th, by 10 a.m., you need to have completed your functional programming readings.
And ensure your perusal annotations are done before class. This reading marks the transition out of pure OD as we begin evaluating those new language families.
Then, the massive one. Monday night, April 6th, by 11:59 p.m., Lab 8 is due. This is the AST Decoration Lab.
Yes. Abstract syntax trees are deeply tied to the concepts of types and class hierarchies we have been unpacking today.
Decorating that tree successfully requires a fundamental grasp of how these elements relate to one another mechanically.
Finally, looking ahead to Friday, April 10th by 10 a.m., you have reading from the compiler's book, skimming Chapter 10 and reading Chapter 11 deeply, again with perusal annotations required for Chapter 11.
It is a packed week. But mastering object-oriented design is the structural foundation that unlocks everything you will be doing with AST decoration and evaluating functional programming paradigms.
It all connects back to the core mission, managing complexity.
We want to thank you for joining us on this deep dive. It really is an elegant journey. From the absolute chaos of the 1970s software crisis, where developers were drowning in procedural spaghetti code,
Right.
to Barbara Liskov's brilliant ADTs locking down memory, and finally to the robust, dynamic, object-oriented structures we rely on today.
It highlights how human ingenuity constantly adapts to the limits of our own cognition. We build abstractions to hide the noise so we can focus on the signal. But if we connect this to the bigger picture outlined in the syllabus, it raises a critical question about the immediate future.
You are talking about the AI integration. the class having access to an LLM API through BitBuddy.
We established that the 1970s software crisis birthed abstract data types because humans were generating imperative code faster than they could mentally manage its complexity.
Yeah.
Now we are entering an era where large language models allow us to generate massive blocks of object-oriented code at 100 times the speed of a human programmer.
We are not just building skyscrapers manually anymore. We have machines generating entire cities of code overnight.
So the provocative thought I want to leave you with is this. If the sheer volume of human-written code caused the first software crisis, are we currently on the verge of a new software crisis driven by the invisible complexity of AI-generated code?
Oh, wow.
And if we are, what will the next level of abstraction look like to save us from it?